This video is going to be about concentration. It's probably a term you've seen before in middle school. So concentration is a qualitative term, and that's not really good enough for chemistry because we usually like to have quantitative results. So I like to use this Kool-Aid example. As you can see on the far right, our Kool-Aid has so much sugar in it that it is quite red. Right, it is a very, very dark red, almost black on the screen. Whereas the Kool-Aid on the very far left has very little sugar crystals in it. And so therefore it's pretty much just pink water. Whereas most people would somewhere veer between these two guys, maybe in the center one, but it depends on your age really. When you're really young, you can usually handle a lot sweeter things, so you kind of veer towards these two guys. And then as you get a lot older, your taste buds change a little bit. At least in my experience, I've noticed that, and I've kind of come to think that that's probably why grandparents, at least most grandparents I've kind of been around, find that a lot of more modern stuff is a lot sweeter. Maybe it's a product of what they grew up with, but regardless, I know with my grandmother, whenever she would make me Kool-Aid, it was almost always somewhere between these two guys. Right? It's basically pink flavored water. It just leaves you with sadness. There's no Kool-Aid in there. It's just pink colored water. If I was 5, I'd probably be making Kool-Aid looks like this. You just keep adding sugar crystals and you make it concentrated, very, very concentrated. If it doesn't have a lot of sugar crystals in it, you would call it dilute. Now, these are very subjective words. So therefore, we're going to have to actually find quantitative results for concentration. And that's what chemists like, quantitative values for concentration, right? Because one person's diluted, like say this one, is my grandmother's concentrated. She would think this was way too sweet. So it's subjective, which is why we have to fall back down to mathematics. So concentration is the measure of the amount of solute that is dissolved in a given quantity of solvent. So solute would be, if I go back to that Kool-Aid example, solute would be the sugar. Solute is the object that is being dissolved. So solute goes into the solvent. Solvent is often water in chemistry because water is one of the better solvents across the earth. If you ever work in a mechanic shop and you go, that's not what solvent is. Water doesn't dissolve things very well. Again, if you're in the mechanic shop, you're working with grease, and grease was specifically manufactured to not be dissolvable by water. So in the mechanic shop, the solvent is quite a bit more. Well, it's not water. It's Varsol. It's something that's meant to dissolve grease. But as far as these words are concerned, solute. This sometimes helps people remember. Goes into, make a little bit of an arrow, goes into the solvent. So you're using the V in solvent. It's kind of hokey, but sometimes it helps kids remember. Solute goes into the solvent. So that shouldn't come up too much though. When it comes to finding quantitative results, we know the concentration in blue is equal to the amount of solute divided by the amount of solvent. So the amount of solute is typically going to be in the number of moles, and the amount of solvent is going to be a volume. So if I actually look at the equation, concentration C is equal to the number of moles, N, so number of moles, divided by the volume, V. So the units for concentration is going to be a mole per liter. Okay, so we call that the molarity, which is a big capital M. All right, so whenever you're doing your math, by the time you're done, if you end up with a mole per liter, you can just substitute that with a big capital M. So molarity is the expression we use for concentration most often in chemistry. So very often they'll ask for, well, what is the molarity rather than what is the concentration? So they kind of throw those back and forth, kind of like how sometimes when you're looking for the mass, sometimes you'll just say, hey, how many grams is that? Rather than, hey, what's the mass of that? So molarity is a very similar thing. So what is the molarity of this solution? So that's just another word for concentration because it is the unit for concentration. Okay. So I've got 3 problems that I'll walk you through real quick. So problem number one, if water is added to 2 moles of glucose, glucose being basically sugar, well, it is not basically, it is sugar. Um, to give a 5-liter solution, what is the concentration? Start off with what's given to you. You know that you have 2 moles, so your N, your number of moles is 2, and your volume would be 5 liters, so 5.0, keep 2 sig figs. So the required is your concentration. So the equation involved is just N divided by V. Okay, so basically you just take your 2 moles divided by your 5 liters. Do some fancy mathematics, you get 0.40 moles per liter. So once again, we keep that extra 0 because of rules of significant figures or sig dig. So there's 2 here. So we keep that trailing 0. And then because we have a mole per liter, that by definition is molarity. So it's really that simple. And if I'm going a little bit too quick in this video, just hit pause. You have that ability. Example, if I give you a mass, so sometimes it's a bit of a pain in the neck because, well, in this case here, like sodium chloride or salt, you're going to be measuring that in terms of a mass. That's the easiest way to measure that kind of a value. So it says a saline solution contains 0.9 grams of sodium chloride in 100 milliliters of solution. What is the concentration? So start off with what's given. You know you're given mass 0.9 grams of sodium chloride. You're given a volume of 100 milliliters. So by definition for concentration, you don't want to work with milliliters, you want to work with liters. So you'll have to do the conversion, the metric conversion right off the bat. So to convert from milliliters to liters, you just move the decimal place 3 times to the left. So that's how we got 0.10. And because there's an underline to that middle 0, that means this 0 here is significant. And so therefore we keep it once we move it over to the decimal. So we need our concentration. So the equation for that again is the number of moles divided by the volume. But here's where we have a problem. We only know the volume. We don't actually know the number of moles. So from that, we're going to have to go back class and actually get into our conversion factors. So we're going to have to use the molar mass to convert our mass of sodium chloride into a number of moles. So here's our conversion factor. This is probably the last time we'll put it in a presentation because for the most part after that previous class, I kind of just expect you to default find this guy in your notes. So, but anyways, if we're going from mass to moles, I use this as a quick little reminder. When we're doing our conversion factor, we're going to basically have to divide by the molar mass, right? We just have to figure out what that molar mass actually is. So to figure out the molar mass, we would just take the mass of molar mass of sodium added to the molar mass of chlorine, right, which is 23.99 grams per mole, added to 35.45 grams per mole. And again, you can just find that on the periodic table. So you should get a total of 58.44 grams per mole. And then from there, it's just do your mass conversion. So take the mass that's given to you, divide by the molar mass. When you divide by the molar mass, the 1 mole goes up top, just like in that flux capacitor that I flashed on the screen there. And so you do a little bit of math, you cancel out the grams, you cancel out the appropriate units. So 0.9 divided by 58.44 is going to be a small number. So I just wrote on the screen here the number to 2 significant figures. I think the next number after the 5 was a 4, but I don't remember anymore. But when you're not done doing calculations, like this is just an intermittent step, typically keep a few more digits in your calculator. But I only wrote down 2 because that's all I really have. So we got 0.015 moles. Now we can actually continue with our concentration equation. So I can put that into my concentration equation, and I end up with 0.015 moles divided by 0.1 liters. And that's just a quick little bit of a math, and you'll just have to end up moving the decimal place 1 over. And I have a mole per liter, so by definition, that means I convert that into a molarity. So my concentration would be 0.15 molarity. So the last example that I'll do with you in this video would be a salt solution that has a concentration of 2.8 molarity. So this time you're given the concentration. And what are we going to find? So it says that the solution contains 0.7 moles of sodium chloride, so same substance again. What is the volume of the solution in milliliters? So this time we're looking for the volume. Okay, now we have concentration, we have the number of moles, so we actually don't have to do what we did in the last question where we solve for the molar mass of this. So we don't have to because we weren't given mass, and since we weren't given mass and they're not asking for mass, we don't have to figure out the molar mass. So that's something to kind of remember for the future. So given the number of moles, we've got 0.70 moles. We have the concentration of 2.8 molarity. So we need to find our volume. The equation says our concentration is the number of moles divided by the volume. So we have to do a little bit of switching around here. So we're just going to do some cross multiplication. We're going to multiply both sides by my volume. So that's basically bring that across the equal sign, then divide both sides by my concentration. And so that gets rid of our volumes and that gets rid of our concentration, or you just switch your denominator with your numerator, whichever works better for you. So our equation for volume is the number of moles divided by the concentration. So we've got the two numbers involved. So 0.7 moles divided by 2.8 molarity. We would convert our molarity into a moles per liter solely so you can just see how the moles cancel out, right? And we have a per liter in my denominator. And whenever you have a denominator inside of a denominator, it just flips up to the top. Right? So that will give us, do the quick little bit of math, 0.7 divided by 2.8, you'll get about 0.25 liters. Now the question wants to know what it is in milliliters, so we'd have to just move the decimal 3 times to the right because we'd be moving from a milliliter up on your metric prefix chart to a liter. So that means you have 3 jumps. So you move it 3 times to the right and you have 250 milliliters as your actual volume. Now we only needed 2 sig figs in the end, so I don't need to put an underline under that 0. It's just 250 milliliters and you're done. So you'll have to solve some problems like that. There's 3 pages that correspond with the assignment. It starts with calculating concentration, and you should find it somewhere in your package. I forget what page number it is. And if you don't have it, I'll just give it to you in class next time I see you. So thanks for watching. And if you have questions, just send me an email.